Right. So there's no hands-on project to go with this chapter. This chapter is about basically the concepts used in these training methods. So feel free to call out questions as we go along. We're going to talk about these techniques, linear regression and gradient descent, and some other techniques as we go ahead. These are just ways to take training data and improve your model to more accurately reflect the training data. So in the old days, this is what I did literally 50 years ago, of course, is fitting lines and polynomials to data, which you can do in closed form equations. All you have to do is sum the squares of the y values and such. There's a well-known way to do straight line and polynomial fits to data. But if you have a more complicated situation, like a measure, like a bunch of real images you're trying to train on, then they don't necessarily fit into a nice, simple mathematical model. So you do gradient descent, where you take little steps in the direction of lowered error to get to the bottom, and there's various ways to do it. So linear regression, we talked about this one before. You might want to put a straight line through the life satisfaction to try to predict how happy people are as opposed to the deduced from the GDP of their country. So you'd have a linear regression model prediction where you just have a offset and then a linear parameter on all of the input data. So that's a straight line in whatever many dimensions you have of input data. And so the cost function, the classical cost function, is the sum of the squared deviations. So the actual observed output, the difference between that and the predicted output, and you square that and add them up. And that's your cost function, which shows how much you're missing the data. And you can express it in matrix calculation with X transform X and so on. And when you're done, you get things like this. And it's very good for problems like this, where you have something that really is a straight line plus noise. You can quickly calculate the best straight line to go through the middle of that. And this is what's done in typical physics and chemistry and normal science like that, where you really have simple dependencies like this. So in the computational complexity, it's something like order of n to the 2.4 or n to the third, where n is the number of samples. This is how much computation time it will take to calculate it. So doubling n will increase the computation time by a factor of 5 to 8. And just like large language models, even if it takes you a lot of effort to compute the model, using the model is easy after that. Even if you had to do a huge amount of calculation to find the best line, you can just program the best line. And that's why large language models that are trained on an unthinkably huge amount of data from the internet cost something like $40 million to train. But once you've determined the parameters, you can run them on a cell phone or a desktop. Using the model is not very computationally expensive. So if the closed form equation fails, then you've got situations where things are more complicated than that. Then you have to use gradient descent, which is a more approximate iterative process than the old-fashioned analytical one that will just immediately get you right to the line by just calculating sums of the data points and the squares and so on, calculate them. So gradient descent works like this. You have some kind of cost function and you have some parameters and you're somewhere and you're trying to find the minimum. So you just start where you are, use partial derivative calculations to figure out what direction will lower the cost, and you take a step in that direction and then do this over and over and over. And eventually you get down to the minimum. If you're lucky, if you have a nice convex curve like this. Now, of course, you might have a more complicated curve where you get stuck in a local minimum and there are problems, but that's the process of gradient descent. Now, if your learning rate is too small, you spend a lot of computer time taking a lot of little steps and you never get there. But if your learning rate is too large, you skip over the bottom and go up here and you end up diverging, where you start here and you end up going here and here and here and here, and things just keep getting worse and worse. You never make it to the bottom. So the learning rate has to be in a reasonable range or it won't work. And so there are pitfalls. You might get stuck in a local minimum where there's in fact a better minimum somewhere else. You might end up on a plateau where the steps are just really, really small and you never seem to be getting anywhere. These are things that can happen. So the mean squared error is a convex function, which is nice. If you have the mean squared error, then there's going to be one global minimum and it will be monotonically increasing around it, so you won't get stuck in a local minimum. So that's nice. Now, you would like to have a continuous function, and this follows that property too, where there aren't any cliffs. There's a smooth slope, so if you roll down the slope, you will be moving towards the bottom. Now, one problem is feature scaling, and we're going to hit this in a lot of the projects. Because a lot of things you get in the form of raw data have a certain scale that may not be optimal. If your minimum is nice and round like this, then you move right towards the bottom. But if one of these features is measured in units that are, say, 10 times bigger, then in fact, the convergence will be much less efficient. So this is a problem, and we're going to see this over and over. So you typically have a scaling step to scale all the measures of your model, your data, before you try to fit it. And then you can do batch gradient descent, where you use, this uses the whole training data at each step. So you have to do this sum over all your training data for every step, and that is a problem. That can mean a whole lot of work to do every step. So you can try various learning rates. Here's learning rate too low, where you go step, 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 and you still haven't made it. Here's a good learning rate. This eta is the step where you take steps, and after a reasonable number of steps, you converge. And here's the learning rate too high, where you just get worse and worse with time instead of better. And so one thing you do when you don't know any better is you just try grid search. You just try various values of the learning rate and see which one produces the best answer. So stochastic gradient descent is where you pick a random instance in the training set. You don't want to bother using all the data. That's too much work. So you pick like a random sample of a small set of the data for each step to move forward. And this turns out to be much faster, and you can use huge training sets now because you don't really use all the training set for every step. And so the cost does not decrease with each step. And so it'll kind of bounce around kind of randomly, because you may not get it, since you're not using all the data, you won't get an accurate determination of what the best direction to go in is, but you will be biased towards the correct direction. So you'll take a sort of jagged path, which mostly goes in the direction of decrease, but not always. And this turns out to be acceptable because the calculations are much faster. And it can even jump out of a local minimum because there's some randomness in it. You might not get stuck in a local minimum. So you got a learning schedule, and what you typically do is gradually decrease the learning rate. So you might take big steps when you're far from the bottom and then take smaller steps when you get there. And this is close to simulated annealing, which is another learning technique where you have like a gas, you put it at a high temperature so things are randomly moving around a lot, and then you cool it. So you lower the random motion to try to get it to settle down to the minimum. You can also do shuffling. You can use one category of data, then switch to another. If your data has groups, you wouldn't want to randomly accidentally use a biased sample. So you shuffle the training data at each epoch or pick the instances randomly, trying to get an unbiased random sample of the subset of the data to use for each step. And there's mini batches where you use small random sets. This gets a performance boost. All right. And so here's an example of this. The stochastic gradient descent wanders around a lot, eventually gets here. And here's the mini batches. And then there's the batch technique where you actually use all the data for every step. And that will, of course, be the most deterministic, the most smooth motion right towards the bottom, but the highest cost. All right. And then this, you can consider how you're going to handle nonlinear situations where this linear model is not good enough. And it turns out that it's incredibly simple. If you've done science, you know, if you have something that's a straight line, and then you have something that's another function like exponential, you use log paper. You just use different paper to make it straight. And that's what you do here. You create new features that are calculated from the other features. So if I have a quadratic function I'm trying to fit, I can't put a straight line through it, obviously. What you do is I have two parameters here, x1 and y. What I do is I create a new parameter as the square of x. And now it's linear in the square of x. Now the polynomial equation, which is a parameter times x squared plus a parameter times x plus 1, is now a straight line in this three-dimensional space where x1 squared is just a parameter. So that's just like using a different kind of graph paper. And it turns out almost anything can be reduced to a straight line by doing this kind of scaling, creating new parameters. I don't think I'll bother with the Kahoots. And so there are learning curves where you're trying to fit these blue dots and you have various polynomials. So here's a 1-degree polynomial, a straight line is the red line trying to fit this data. And as you can see, that's not really catching the trend of the data. A 2-degree polynomial is the best. That's the blue line that really goes through the data. And as I mentioned before, you could fit a really high order polynomial, 300-degree polynomial, and then you get this wildly oscillating thing, which of course gets pretty close to the data. It even tends to spike the noise in the data. And this is where you just have to add like some human judgment. But cross-validation will help, determining whether the data really, where all the oscillation is really justified. Your cross-validation, where you train on part of the data and evaluate on the rest, would detect that this is not, in fact, a better fit than the blue dashed line. So you have learning curves, which show you how many iterations it takes to train the model. And so here you are, and you can also consider changing the training set size. So your model can be perfect for just a few training sets, but once you add more data, it'll train out. And hopefully your training data and your validation data will converge together to the same ultimate error. That's if things are converging to a good fit. Now, if you have, if you do a 10th degree model for quadratic data, this is overfitting. You're now using a far too complex model that fits the noise in addition to the data, and therefore your training data you'll have a small error, but your validation data will have a higher error that doesn't converge, which means your training is overfitting. It is making a model that is too specific to the training data that does not generalize to other data. All right, and so you have bias caused by wrong assumptions and such. You have variance where you have overfit the training data, so you created a false trend that's not real in the actual population the data was drawn from. And then there's the irreducible error, which is just the noise in the data. And so if you increase a model's complexity, you get more variance and less bias. So linear models, you just can regularize the model by trying to prevent it from introducing unnecessary wild oscillations. So there are various ways to do this to lower the jaggedness of the model. And here's various ways to do it. Ridge regression is where you add a cost function to it. Here's the error. Your mean squared error is fitting the data, and then you just add a penalty for having large parameters, which is steep slopes. You just add this to it, so it will be biased towards lower values of the parameters, which would be less jagged data. That's the idea. And this hyperparameter alpha determines how much you're going to stomp on the model to smooth it, and therefore accept a less perfect fit to the data, but a more smooth fit. This is called the L2 norm, using the square of the weights. And so here's various levels of ridge regression. If alpha equals 0, you get this fit, but as you smooth it, it will hit shallower lines through this data because you told it to favor lower parameters. And here at a polynomial model, it's more obvious why you would do this. With alpha is 0, you've got one of these models that waves around too much because it's fitting the noise in addition to the data. So adding the regularization parameter causes it to choose the smooth fit through the trend, which is probably what you really want. And then there's the lasso regression, where instead of using the square of the parameters, you use the absolute value of the parameters. So it has the same general effect. All right. And you can see it essentially the same here. Again, it'll move from this wavy line to the straight line at a certain level. Looks like in this case, 0.01 is probably the best fit, where it still does rise to follow the data, but it doesn't jump up and around. This alpha equals 1 has forced it to just be a constant value ignoring x1, and that's too extreme. That's missing the trend. And then you got elastic net, where you just mix the two. You have the squared parameters and you have the absolute value parameters, and you have another parameter to see the relative contribution of those. So you have two meta parameters, alpha and R, and you can adjust them both to try to find the amount of regularization that will make a good fit for your data. So no regularization at all is usually a bad choice, and there are various techniques. Situations in which people like them. If you suspect that only a few features are useful, then they say Lasso or ElasticNet is good. ElasticNet preferred over Lasso. This is just in practice with data. These different techniques have, you might need them different ones for different models. And I talked about this before. Another way to regularize gradient descent is to just stop as soon as you hit the model, the minimum. So you have your validation error, and as soon as that starts going up, then you quit. Even though you could keep training and your training set error would go down, if the validation set is not improving, then you're probably overfitting. You're fitting the noise, not the data down here, so you quit as soon as the validation set stops improving. So there's logistic regression. This is another way to do it. So if just what we've got, you have some kind of output, and if the output is greater than a threshold, then you call it positive. So you have some measure of how spammy is this email, and if it's above a certain threshold, you say it's true that it's spam, and if it's below, you say it's false that it's spam. So you typically have a logistic function for this, where you have a continuously varying parameter that might go over a wide range, but the output just goes from 0 to 1, the probability that this thing is spam. So this is one of the functions you can use to convert a continuously varying value over a wide range into a value that just goes from 0 to 1, which is what you want. And so here's the cost function of a single training instance. You can use the log of it here. So if your model has a low probability for a positive instance, that's a high cost, and so on. You get a large cost if it's making drastic errors. All right. And there's a logistic cost function as well. All right. I forget the details of this. I'm not going to worry about it. Let's talk about a case here. This is a very famous machine learning model where they tried to determine these 3 species of irises by measuring properties of the flower. So there's a petal size, and there's something called a sepal size, and there's some other measurement you make. And from those measurements, you can separate them. So there are 3 features: sepal width, sepal length, and petal length. And seems to be a 4th one: sepal width, petal length, and petal width. Yes, you don't use sepal length for some reason. These are the 3 things you use to try to predict which category of 3 species of irises there are. And so here's an example. Here's petal width, and the blue is one of the species, and the green is one of the other. So in general, this one is larger, but there's overlap. So when you move a threshold, if you put a threshold here, you'll have this decision barrier, and so this decision function. So the point is, you can't perfectly isolate them with just this one measurement, but you can have some success. And you could adjust this threshold just like we've done before. If you put the threshold way up here, you will never misidentify the blues as being green, but you'll misidentify a bunch of greens as being blue. If you put the border down here, you'll get all the blues that you call blue are in fact blue, but you'll have these blues you'll misidentify as the green category, and so on. So you can define that here with petal length and petal width, and here are the 2 categories. And so you'll find the line here, the dashed line is 50% probability, where you have the balance between false positives and false negatives. That's the sort of thing you have there. All right. Anyway, that's what I wanted to tell you about that. Let me stop this video.